Again, the principle is stop me anytime when you have a question. You don't have to take notes because I'm going to post the notes and the lecture video online really quick. So focus on listening and focus on questions. Otherwise, if I go too fast, as I said, I'm going to cover calculus too. Okay, you like it or not. Okay, let's talk about calculus. Calculus 1. So basically, a lot of people ask what calculus is about. My personal understanding is we start with a question. Let's take a stick. Okay? And then for the first day, we take the stick. The second day, we cut it by half. So we only have half left. The next day, we cut it by half. So we only have this much left. So as you can see, every day, this stick becomes shorter and shorter and shorter really quickly. Now assume we just keep doing this forever until the end of the universe. In other words, as time goes to infinity. My question is, eventually, at some day, will this stick disappear? It's just like you cut the last drop, and then after that, you can't cut anymore because it's gone. Okay? Go to the button where you raise your hand. If you think the answer is yes, it will disappear. Just press the yes button. And if you think it's no, just press no. Got no, no, no. Let's see if I have a yes. Jordan? I saw you answered yes. Can you tell us like what you're thinking, why you think it's a yes?
You can hear me? Yeah.
Yep.
I would just think if you go to infinity, it's eventually gonna disappear because you're going to infinity. So it's hard to explain, but like if you keep going forever, it can't exist because
So let me ask you this question. When will that thing stop existing? Or when will that thing disappear? A million years?
It has to be at infinity because a million years there would still be a tiny piece left.
Right. So actually, it's hard to quantify because if you say it disappear, you need to say the time. But then it seems like the time, we will never reach that time.
True. Yeah, correct.
Then is it fair for me to say, like, since we could never reach the time it's gone, then it's not gone. It's never gone.
Yeah, sure.
Right. So what you said, number one, is not wrong. Actually, this is a really hard question. But I also try to argue that this one not disappear, which I think is the reason why most people just picked no. Right? It's roughly just like there will be some piece left because you could never run out of time. So it will never be gone. Okay. With that in mind, with the majority saying it will not disappear, but we do have some valid argument about it will disappear. Let's transfer this one into a mathematical problem. That is, if you have 1, and then you divide the number by 2, which means we'll cut by half. We got 1/2. And then you got 1/4. And so on. You got 1/8. Keep cutting by half. And eventually, will this one disappear? Is simply asking a question. Is this one 0? Eventually. And do you feel like it's the same analogy? If this one will never be gone, this one will never be 0. Right? Actually, a little bit bigger than 0, if I could. Make sense so far? And for the people who's answered yes, then your answer should be yes, this one is 0. Okay, that's the analogy here. Good. Then the follow-up question is, if in the end it's not 0, then what is it? How much? How big is the number? Is it roughly the size of 0.001? Way smaller, right? Is it roughly the size of 0.000000001? Eventually, it will be smaller than that. Does that make sense to everybody? So here's the thing. Actually, this one is, how big is it? It's smaller. Smaller than what? Smaller than anything you just named. And you will name later. But somehow it's not 0. Do you agree? Does it feel all right? Does it feel wrong? Like smaller than anything, that thing should definitely be 0. But now you're telling me there's something there which is not 0, but also smaller than anything you name. That's kind of strange, right? The first time you think about it. Cool. Let's keep going. So we agree something can exist. It's very, very small, smaller than anything, but it's not 0. Let's try another mathematical calculation. Does everybody know what 0.9 with a bar means? It's 0.9999, right? And how many nines? Forever, infinity. Okay. Well, of course, we know 1. And we know this one is very close to 1. Now the question is, which one is bigger? Is this one less than 1? Or is this one the same as 1? If you think it's less than, try to say yes. And if you think it's equal, try to say no. And let's do the vote again. We got a lot of yes. We got a few no. Okay, let's go with yes. Let's call Austin. Why do you think it's yes? Which means this one is less than.
I think it's yes because just 0.99 is just like, I know you can round up to 1, but it's still like less than 1.
Or moreover, it's actually 1 minus 0.9 bar is going to be 0, 0, 0, 1, but actually not 1 here. The 1 is still later, right?
Yeah.
And then 1, but not here, but keep going. So eventually you just keep going. And somewhere you are going to have a 1. Eventually this one is something smaller than anything you can name, just as the thing before, but clearly it's not 0. As long as it's not 0, there's a difference between these two. Therefore, this one is less than. Does it kind of grab your thoughts?
Yeah.
Okay. Everybody agree who answered yes? Now let's turn to people who answered no. Adam, why do you think it's no? Which means you agree with this one is equal to this.
I mean, like point. So like if you take 1/3, I mean, I've seen something similar to this before, where 1/3 is 0.3 repeating. So 0.9 repeating is 3 times that, which is
Let's write your
2/3.
thought down. So you're saying everybody know 1/3, all right? And everybody know 1/3 is 0.333 repeats. Okay. Now what is? They're the same. But here's the question: what is this one times 3? That should be 0.9999 because before that was 0.3333. Make sense so far? Okay. What is 1/3 times 3? That should be 1. Still okay? You start with two things which are the same as each other. You time both by 3. Then they should still be the same with each other. Does that make sense here? Okay, Adam, is that what you mean?
Yeah.
Okay, and from here, clearly, if you trust mathematics, they are the same. Because 1/3 is 0.3 bar, and if you have an equal sign, you time the same number on both sides, you should still have equal sign. So they has to be the same. Otherwise, multiplication fail. Then you cannot trust anything. You cannot trust 2 times 3 equal to 6 anymore because multiplication has flaw. Sounds good? Okay, one answer clearly makes sense. This one is just some 0, and eventually you're going to have a 1, but you will never reach that 1. That's something smaller than anything you can name. And according to our concept before, something smaller than anything you can name, but it is not 0 by common sense. Here, it should be 0. This is by mathematics. Okay, now we know at most one of them is right. The worst case, both are wrong because they don't agree with each other, right? Okay, so what's your deal? Do you want to say, sorry, I cannot trust my sense, or do you want to say, no, I don't trust mathematics? Either one is a very big flaw. Either one is a very big collapse for how you see the world. Kind of make sense here? And it's not only you. This actually bothered people for 1800 years. So many things was around this, and they just couldn't explain. Okay, but let's summarize what we have here. Why is those kind of problem hard? And the reason is because we're dealing something really, 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 really small. We gave it a name. We call it infinitesimal small. And if you try to imagine it, this is something you could never deal within finite frame of work. Since something like finite time, finite value, you have to push this one to infinity framework. Because we use again, again, and again. We use never stops. We use eventually. We use in the end. You never stop, right? Forever. We use those kind of words. So that thing goes to infinity. And that is the reason why it's hard. Now, calculus is exactly the branch of mathematics which handles those kind of extremely small things. And also, things are extremely big. And eventually, we will try to prove they are actually closely related. At a philosophical level, that is what calculus deal with. Make sense here? Okay, that's kind of shaky, right? It's just like, oh, that's good story. That's good theory. What is it useful? Well, number one, a lot of things relies on that. For example, how wide is the line? What's the width? 0, right? That thing has no width. I'm talking about a theoretical line, not a real line we draw with my pen. Okay, it's a theoretical line. That thing has no width at all, right? Another thing to say, this one has no area at all because you're only a line. Good so far? Okay. But now, what about the area of a rectangle? Certainly, that thing has an area. For example, if it's 1 by 1, the area is 1. Now, here's the question. Do you agree that the rectangle consists of a lot of lines? And basically just lines, right? Nothing else. And each line has no area. Somehow you put a lot of something which has no area together, that thing suddenly have an area. Kind of makes sense here? That's strange. So, of course, mathematics use this. But now you think about, even in real life, we actually need to think about things like this. And that's where things get interesting. This is philosophical. It's kind of interesting, but not useful. But now in real life, we actually need to think about this, and I will give you an example. It's very useful. It's actually everywhere. The thing we're trying to do with this is called the changing rate. Later, we will show this one has a name, which is called the derivative. Okay? Changing rate is something very simple to understand. Let's say today is 58 degrees. Okay? Let's say you have that data. You wonder, what's going to be the degree tomorrow? Is it going to be 59? Is it going to be like 57? Okay? From the moment you start to ask a question, that is, what? Not only I know the value of the function, I want to know what's the changing rate. Is it going to be increasing? Is it decreasing? Okay. And also you want to know how fast is it going to decrease or increase? That is actually the question of changing rate. If it's increasing, you have a positive changing rate. If it's decreasing, you have a negative changing rate. If it's doing really fast, it's changing really fast, you got a big changing rate. Okay, and if it's changing really, really slow or barely changes, you have a changing rate very close to 0. In other words, very small. Good so far? Now let's see how do we calculate this thing, which is called changing rate. There are changing rate of temperatures. There are changing rate of stock price. And if you know that, you can predict the stock price. You can make a lot of money. Okay, but now we're going to focus on a classic example. That is the changing rate in physics. Moreover, the changing rate of distance. Do you know the name for that? What's the changing rate of distance? Velocity. Believe it or not, velocity is actually a changing rate. Sounds good? Let's see how we calculate this. Let's say I'm in lacrosse. and I want to go to Madison. I start at 2 o'clock, it ends at 4 o'clock. Okay, arrive there. My question is, what is my changing rate? Or what is my velocity? At 3. Okay, 3 o'clock, right half the way. How fast am I driving? How do you do that? We use a formula. Velocity equals distance divided by time. All right. Now I Google. Online, La Crosse to Madison is roughly like 120 miles. So the distance is 120 miles. To get the velocity, I need to take in consideration of how long does it take me to drive 120 miles. It took me 2 hours, which is from 2 to 4. So I got a velocity, 60 miles per hour. Good so far? Is that the velocity? Is that how fast I'm driving at 3 o'clock? Is it? Not really, right? This actually is not a velocity. This is something called average velocity. That means roughly, more or less, you drive 60 miles per hour during the past 2 hours. That means sometimes you may drive 59, sometimes you may drive 72, sometimes you may drive 30 miles per hour, but altogether, if you smooth everything out, it's going to be 60. Good so far? So there's no way this one can tell what happens at 3 o'clock particularly. So this is not a good one. But this is the only formula we know. So how do we make it more accurate? This is what I'm going to do. I'm going to take the same formula, but this time I'm going to take where I am at 3:30 minus where I am at 3 o'clock. That's how much I drive in 30 minutes. Okay. Then I divide by, instead of 2 hours, I divide by 30 minutes. Do you believe this one is better than what we had before, which takes 2 hours? We take the average. Now we just take the average of 30 minutes. It's better. Right? Is it accurate? No, because we can still do better. How do I do better? I think you start to get the idea. Let's do 3:01 minus what we had at 3 o'clock and divide by 1 minute. If I were you, I would be happy now. I mean, within 1 minute, I measured that thing. That's pretty damn accurate, right? But can you do better? Well, I can. I don't want to. 3 o'clock, 1 more second, minus this, divided by 1 second. It's better. Now question, can you do even better? Do you see where this is going? As long as you stop, it's not the right answer. When will you get the right answer? When this one keep going and never ends. Until you are basically dividing by a very small interval that is 0. Then everything got settled down. Now you have the accurate thing, which happens at 3. You start from 3, you end at 3. Sounds good? That's the idea. This is how people measure real distance in real life. They stop somewhere. You know, they stop at 1 minute. They say, that's it. I know it's not accurate. It's not too far from the real one either. But in mathematics, you want something really accurate. So we need to push further. Now let's summarize what we just did. Basically, we have a displacement or distance denoted by ft, which is a function of time. You plug in 2, you got your distance at 2 o'clock. You plug in 4, you got 4 o'clock. You plug in 3, you plug in 3 and 1 second. You got all the displacement people have. Good so far? Now, you consider this one. You wonder, what is the velocity at time? And let's not use t, use x. x equals a. What happens at 3 o'clock, for example? But I can also ask 3:30, whatever. So at time a. Now, how do we do it? We use the distance divided by the time. In order to do that, we need to consider a time interval. For example, if you want to consider 3 o'clock, you take your a to be 3, but then you consider 3 o'clock to 3:30. If that's not happy, 3 o'clock to 3:01, and keep going. Right? That's the interval you are considering. Now I'm going to use an abstract notation, which is the starting, okay, and the ending. And here we have a time interval h, basically represent how long the interval is. For example, 3 to 3:30 basically means I start from 3, I end at 3 o'clock plus 30 minutes. Therefore, my h is going to be 30 minutes. From 3 all the way to 3:01, which is basically 3 o'clock plus 1 more minute. Then my h is going to be 1 minute, and go on. Good so far? Then the formula becomes distance in the end, which is at a plus h, minus the distance at the starting, which is a. That's how much you drive during the past h time. This will be my average velocity. Okay, you take h to be 2 hours. That's the first case we talk about. You take h to be 30 minutes. That's a better case. You take h to be 1 minute, 1 second. It's better and better and better. Good so far? Now, when will this velocity, will this average velocity become the real instantaneous velocity? Or let's just say equals the formula just now. When will this one be accurate? That's when h is extremely small, right? That's when h goes to 0. Okay, if h is 1, it's accurate, but not so accurate. You can do better by assigning h to be 0.1. You can do even better by assigning h to be closer and closer and to 0. So when do you reach the right one? That happens at 0. Good so far? We call this process taking the limit. We let h goes to 0. We write an arrow to say goes to 0. And then the notation is given by limit. H goes to 0. And when h goes to 0, whatever this is, it's going to be my velocity. Sounds good? Cool. Back to our question again. This h goes to 0. Is h 0? Okay, let's take a poll. If you think h is 0, take a yes. And if h is not 0, answer no. Okay, let's try to do that. Most people answered no. Oh, actually, everybody answered no now. Yeah. Okay. Let's call random. Addie, can you say something about why you picked no, which means you think h is not 0?
Because like you said previously, I feel like as the limit reaches the average velocity at some point, it won't go to 0. It's still going to keep going.
So it is not 0.
It is not 0.
then how big is it?
I don't know. I just don't.
Smaller than anything you want, right? Can you see that we return to the paradox we just did?
Yeah.
That is, you cut the thing by half. How big is it? Well, it's smaller than anything you want, but it's not 0.
Yeah.
Okay. But here's the problem. If it is not 0, that means you have an interval. That means you could always do better than h. For example, you can pick half h. That's certainly better than h. That means if you stop somewhere, you don't have the very accurate answer. Does that make sense to you? Like if you think h is not 0, then I can always do better than you. I just take half your size.
You're right.
Right? Okay, so that's my argument there. Think about it. Who wants to switch your answer now? Okay, Aaron, you switched. That means now you think it should be 0. Okay, and did you switch just because of my reason? Do you think that's pretty convincing?
Well, yeah. Also, I mean, if it keeps getting smaller, you're really never gonna find the true and correct answer.
So there's no difference between you and 0, right? It's basically trying to say like there's no difference between these two. I mean, there is a difference, which is 0, 0, 9, but that thing is 0 because 0.9 bar equals 1, right? The difference between you just doesn't matter anymore. It's the same as 0. That's a very good argument. But now I'm going to ask you a question. Can you divide by 0?
No, that's why I originally clicked no, but because I knew you couldn't divide by 0. But I mean, given that,
Does the problem still exist?
yeah.
You see the problem?
Yeah.
Okay. Another thing I need to ask you that is this: if h is 0, that means what? That means you start from A, you end at A, right? You start from 3 o'clock, you end at 3 o'clock. That's your interval, right? Do you even have an interval? Did you move at all?
No.
From 3 to 3, did you move? If you didn't move, how on earth do you have velocity? You don't even move, right? Can you see the paradox here? Can everybody see the paradox here now? We start from a very useless question, but now you find that thing actually bothers you, even if you find something so simple. Every time you drive a car, the car tells you you're driving at 45 minutes right now, 45 miles per hour right now. You cannot trust it because h is now 0, or h is 0. I don't know which way. Kind of makes sense now? That's the paradox we are trying to solve with the whole class. And from here, at least, I think you have an expression that is, this is hard. We better be careful, knowing that what kind of things we're doing are legal, and what kind of things, when we do it, we make mistake. Okay, that's very careful, because you may very likely, if you treat it as 0 or not 0, you may very likely have different answer. And they may not agree with each other. And the best case, you got lucky, you get the right one. Worst case, you got both wrong. Sounds good? Okay, so that's how we quantify changing rate. Velocity is just the changing rate of displacement. But this formula, you can change your F to be anything. For example, if you change FT to be your stock price, then basically what this one gives you the changing rate of your stock price, because that's the stock price tomorrow minus stock price today divided by 1 day. And then stock price next hour minus the stock price this hour divided by 1 hour. You have the changing rate. Now, how do you get it correct? You let h goes to 0. That's a pretty easy and beautiful analogy. Okay, so that's the first thing. Later we will show this thing is actually called the derivative, which is very, very useful, which gives you the changing rate. Cool. Now we want to understand the same thing, but this time from a very different perspective, because in mathematics, it's always helpful for you to understand the same thing from different perspectives. We know this is a function the moment we write it down. And we know the function has a graph if we want to draw it. Then we can basically redo what we just did, but this time only in graph, no computation. Sounds good? Let's do it. So you have a function. That's fine. The x is your time t. Your y is going to be your ft, which is your distance. At time t, you're at La Crosse, so you have 0 distance. At some t later, you reach Madison. Okay? Then your displacement, your distance follows a certain kind of trace. Okay? Depending on how you drive. Maybe you just drive really fast at first, you got excited. Then you find a cop, you slow down. Okay? And then you just stop there for some snacks. And then you find, oh shoot, I forgot my backpack. I need to come back to my friend's house. I don't know, to pick up my backpack by driving back. And then I keep going, and eventually, okay, I reached where Madison is. The thing can be anything. Good so far? The question now becomes, what is your changing rate? What is your velocity? At a given time, A. What do? You do Fa plus h minus Fa divided by h. That's the formula. We already know this is right. Now we just need to translate it to graphs. What do you mean by A plus h if you know this is A? That's just another point to the right with the distance h. Okay? What is Fa plus h? That is just this point at A plus h. What is Fa? That is nothing but this point at A. Good so far? So let's write it down. The length here is Fa plus h. The length here is just Fa. Now what is Fa plus h minus Fa? That's going to be the difference. And I think we can all see that that's the difference between here and here. That is what's on the top. Sounds good? What's on the bottom? H. What is h? The distance between this one and this one horizontally, that is h. We just mark it. So our h is nothing but how long this is. Okay? So what is this formula when you try to do the average velocity? What you're trying to do is you're trying to use the blue divided by orange. That's what you're trying to do. Sounds good? And we know that. What is that? That is actually the slope of this line. If you connect them, the slope means if my x go the orange distance, my y is going to raise by blue distance. That's exactly what slope means. Good so far? Okay, so we have an equivalent understanding. This is your average velocity by algebra, but really, what it means is the slope of the second line connecting these 2 points, A and A plus H. Here, AFA and A plus H, FA plus H. That's what your formula is. Good so far? Cool. Now let's understand the thing in a different way. What is the velocity at A? This is what you should do. You pick a point, you connect these 2 things, you say, well, the slope of this line tells you the changing rate. Sounds good? According to what I see here, there's no changing rate. You don't move at all. Is it accurate? Not really. Why? Because your interval is too wide. Why don't you just pick the interval to be from here? Oh, shit. From here to here. Let's take the point closer. What do you got? You got another line. This one looks so much better. At least you got the right sign. You are going to decrease later. Good so far? Accurate? No. Why? Because your point can be here. That's going to be even better. Okay, good enough? Not really. Your point can be here, which is even closer. Now, when will you be very accurate? When limit h goes to 0. This. Okay. Right? But what do you mean by this when h goes to 0? This is the slope. When h goes to 0, what happened? When h goes to 0, let's draw another one. When h goes to 0, the starting point and ending point become the same point. Right? Your original line connects 2 points. Now your line only have 1 point. This line only has one common point with this curve. Not 2, only 1. We have a name for such line, do you remember? That's not called secant line anymore. Think about it. You have a circle. You have all kinds of lines intersect the circle for twice, but there's one line. Just barely touch it and do it only for once. That is called tangent line. Sounds good? Okay, then this is the second line, but when you take the limit, this one becomes the slope of the tangent line. So basically when this one tells you, this is what we got for tangent rate. We just figure out it's the same as the slope of the tangent line. That means the slope of the tangent line tells you the tangent rate. Does it make sense? Let's try to draw something. What's the tangent rate here? Positive or negative? Positive. It's going to go up. How did you know? Because if I draw the straight line, this is the tangent line, and the slope is clearly positive. If I'm going to guess, the slope is 1. Good so far? What's the tangent rate? What's the velocity here? Well, it's not changing at all because if I do the tangent line, it's horizontal, right? That means it's not increasing, it's not decreasing at this very moment. Okay, I cannot tell the trend. Good so far? Try another example. What's the changing rate here? You can see it's increasing. What's the changing rate here? It's decreasing. It's all thanks to the tangent line. So from here, we can see it actually makes sense. These two things should be the same. Sounds good? Okay, that's everything. So let's wrap up what we just did. Number 1, we talk about something called changing rate. Then we figured this one has a formula, which is the average change rate, and you let the interval to be extremely small. How small? Limit goes to 0. And then you find this is the same as the slope of the tangent line. Okay. Next time we talk about these 3 things, you just need to reflect they are the same thing. Okay. That also means if I ask you what's the changing rate of the tangent, what's the changing rate of the function, you can basically either go with this formula or you can go ahead and try to find a tangent line and give me the slope. Doesn't really matter which one you give me. Actually, they are going to be the same number. Okay. All these 3 things, they represent the same thing, and we give it a name. That is called the derivative. Okay. And that will be the theme of our first 3 quarters of the semester. Okay. We start with chapter 2. In chapter 3, we talk about derivatives, how to compute it fast. What does it mean? In chapter 4, we talk about applications of derivatives. How do we use that thing to solve real-life problems, to understand phenomena? Chapter 5 and 6 will be called integral, which is closely related to derivatives. But before you can talk about derivative, now you know the problem. And the problem is the one we raised at the beginning. How do you understand something which is 0 or not 0, or meanwhile 0 and not 0 at the same time? Or neither, or whatever, okay? To understand that, we need another chapter before, which is called the limit. Once you know everything about limit, you can use this formula. Once you use this formula, you find all the derivatives. Okay, that's the logic. Sounds good? Okay, be prepared. This chapter is going to be tricky. Computation is super easy. The harder part is try to understand, try to make sense of the content. Okay, and try to see how that thing challenge your common sense. I will give you some example. There's something called Zeno's paradox. Some of you may have heard about it. I'm going to introduce two of them. Okay. The first one is called the Achilles, and the Tityrus. Achilles, we know he's a war hero, but in this case, we're just going to borrow him as a fast runner. Okay, and Tartarus, of course, we know it runs really slow, so slow runner. We don't even want to call it a runner. A slow-moving object. Okay, so here's the thing: if they take a race to go from A to B, Achilles is definitely going to win. Okay, and because he's going to win, he wants to make it more fun. So what he says is, Tartarus, please go ahead and start ahead of me. So I start from here. A stands for him. And Tartarus, you start from here. Okay? Good so far? Now let the race begin. What's going to happen? Well, number one, it's going to take Achilles some time to run to where the Tartarus war was. Okay? Then during that time, the Tartarus move a little bit ahead. But their distance becomes shorter than before because Achilles runs faster. For sure, he catches up. Okay. Now, for the next moment, it will take Achilles another moment to run to where the Tartarus war was. Then by that time, the Tartarus somehow just managed to move a little bit ahead. Otherwise, it stays at where it was. It definitely won't happen because he's moving, right? Okay. Now, it took Achilles some time to reach, again, where the Tartarus was. But then by that time, the Tartarus was ahead a little bit because he also moved. Good so far? So if we take a snapshot like this, again, and again, can you see that in this way, the Achilles could never catch up with the turtle? Okay? Does it make sense, the statement? The Achilles will never catch up with the turtle. Of course it doesn't. Otherwise, why do we do, field and tracks? If you start early, you're done for, right? Meanwhile, why is my logic wrong? If it's wrong in real life, it must mean this is wrong. But why is my logic wrong? Think about it. That's the first paradox. The second paradox. Using the same analogy, Zeno somehow managed, he proved that there's no such thing as movement. There's no such thing as velocity. That's a very bold assertion. But let's hear his reasons. You go from A to B. All right. In order to do that, you have to reach the middle point first. And then go the other half. Sounds good? Then you need to reach the second middle point, which is between the first middle point and the last thing, before you reach B. Still okay? Then you need to reach the middle point here before you reach B. And then you need to take the middle point here before you reach B. And keep going. Does that make sense to everybody? How many stops do you need to make? You don't actually stop, but if you take a snapshot, right? How many stops do you need in order to go from A to B? Infinite many. Because as long as you are not B yet, there is always a half point. There is always a halfway, no matter how small it is. Infinite many stops, and each stop takes time, right? Because it's not zero. It takes some time, small time, but some time. That means infinite time to go from A to B. Okay, let's say the logic. As long as you're away from to B, you have to make a stop halfway. And then you need to make a stop at halfway. And then you need to make a stop at halfway. How many stops are there? There's always a halfway. So there are infinite many stops. And to reach each stop, you need to use some time, right? So that's infinite many time to go from A to B. Therefore, you could never go from A to B. 1 hour is not enough. 1 day is not enough. 1 life is not enough. That's what his argument is. So you could never go from A to B. Therefore, motion, there's no motion. Motion does not exist. Velocity does not exist because you don't move, no matter how close A and B are. Do you see the paradox here? Okay, again, it's certainly wrong. The interesting part is, how do you tell Zeno you're wrong? Without just saying, just look. Okay, he said, I refuse to look. Hey, this is in my mind. Tell me where I went wrong. Otherwise, I convinced you, right? So that's the paradox. And if you take a look, can you see this one is closely related to the previous one, which is how do you deal with infinitely small time? Is it time or no time? Right? Infinite stop, is it distance or no distance? Is it 0 or not 0? Make sense here? And if you can solve that, you can come back and solve this. You can tell you if h is 0 or not. Is that okay if I set h to 0 and divide by 0? Or is that okay for me to keep h not 0, but somehow say you still start from A and ends at A? Therefore, we don't have interval, but then we don't move, but then we don't have velocity. So that's the same problem. And then eventually they all reduce to the very beginning. If you have something really, I can keep going on, really small, is it 0? Or is it not 0? So far, hopefully by following this lecture, you start to feel like both answers are wrong. It is not 0. And certainly, I feel hesitant to say it is 0. But is it even possible that there's a third answer? Okay, think about it. And feel free to come back and talk with me about the paradox, because we're not going to cover it in class. It's just some brain teaser. But it's really interesting to talk about it and think about how people during the past 2,000 years, actually 1,800 years, to develop a deep understanding of how to quantify infinity, which seems like an impossible thing to do. Right? How do you quantify infinity? Give it a number, there's no number. Okay. And moreover, if you have two infinity, somehow you can tell one infinity is bigger than the other infinity. Can you do that? If you have two things extremely small, both have 0 width, but somehow you can tell one line is wider than the other one, even though both have 0 width, but one line is wider. Can you do that? And that's exactly what we're trying to do. And we do have a good reason for that, because we need to quantify changing rate, which is a very simple concept, turns out to be very difficult. Okay, that's all we need to cover for the first day, the introduction. I will give you some room to ask questions. And again, please raise your hand before you ask any questions. Emmett, please go ahead.
Can everyone hear me?
Yep.
Okay. I was just wondering, could you kind of like re-explain the tangent line part? I got everything before that and after that, but my brain just didn't like the...
Do you get the second line part?
Yeah.
If you get the second line part, which comes from this formula, that is associated to this graph with 2 points, A and A plus H, and we draw the line. Good so far?
Yeah,
now the
that
only
makes sense.
difference is from here to here, we add one more thing. That is, we let H goes to 0 for the same thing. From geometry, from algebra, that means the bottom goes to 0, right?
Yeah.
Simultaneously in the graph, that means these 2 points, A and A plus H, both become a because h goes to 0, right?
Yeah, when you say goes to 0, do you mean like an asymptote, like it gets closer?
Haha, that's
Or-
exactly where we get confused. It is not
Or
at a.
okay,
And it's nothing like a plus 0.1. It's closer than that. It's closer than anything to a. But it's not a.
okay.
That's the tricky part.
I think I kind of get the difference. So then what would the actual tangent line be? Would it just be like the
It will be
same?
only there is a point, and this time the red point is the same as a black point. And you still have a line passing both points, which in this case just pass 1 point.
Okay, so that's a literally 0 for h.
Exactly.
Okay.
That's where we get shaky. Like secant become tangent because 2 points become 1 point. And that is because h goes to 0.
Okay, thank you so much for explaining that.
Yeah, great. TJ, just go ahead.
Yeah, can you hear me?
Yep.
Yeah, so I know you said that the homework wouldn't be due till Saturday, but is there
Mhm.
any homework due this Saturday?
No, this is not
No.
even the sections yet. 2.1
Okay.
will be tomorrow. Yep.
Thank you.
Anton?
Kind of piggybacking off of the first question. So you talked about how I'm not entirely sure if we concluded if it, when doing the calculations, if h is going to be 0 or h is just so small. Because obviously it can't be
we kind
0
of
as you
concluded
already
both.
said.
It's kind of
Right.
like, yeah, 0 is not completely right, but not 0 is also not completely right.
Hmm.
So we need something more.
All right, and that's
So-
to be discussed or something.
That's still not there yet because for now you just know one thing, that is my instinct probably is not that accurate.
Got it.
From now you probably stop saying something like it makes sense. Then you need to ask like it make in which sense, because people have
Yeah.
different senses, and some senses are trustworthy and some senses are not trustworthy. Right. So that's why we want to push things to the limit, to the extreme, so we understand the clear difference between yes and no. And don't feel bad if you don't grasp it, because this is only asking the question, not answering it. And keep in mind, it takes people 1,800 years to do that. Brilliant people, okay? Generation after generation. So it's awesome that if you get confused. And even when we finish this class, I cannot claim that you will understand it. I would just say you kind of feel better. It's not like you understand it. It's just you kind of feel better than from the start. And when you really get used to it, you need to actually handle it every day at this level until you get familiar with it, which you will not do unless you are a science student and you choose to pursue further in math class. Okay, so just keep in mind, we're not offering an answer here. Okay, but of course, the computation later, you can just trust it because people did it for you and tell you it's reliable if you do it in their way. Okay, but there's much more gap for the understanding there. Okay, if no question, the class is over. By the way, one more thing. I received an email, but I want to say that sometimes we talk about things even after the class is due. So feel free to leave once it's after 11:55. The only reason I'm staying here is because some of you may have some questions. It's almost like everybody's leaving, but still there are like 2 or 3 kids. They just chose to stay there for another 5 minutes for some additional questions. Okay, so feel free to leave because the lecture will definitely be over before the class time ends. Okay, that's all for today. And please stay if you have questions. Otherwise, yeah, feel free to quit the room. So, yeah.